Hello and welcome to our discussion on kinematics. And we mentioned that kinematics is the study of motion, and cinematics. And these are the four general equations that we need to understand whenever we're trying to calculate a kinematic problem, where D refers to displacement, VI or V naught refers to the initial velocity, T refers to the time, A refers to the acceleration, and T refers to time. So these are four formulas depending on what is the problem presenting you. A problem may give you the final velocity of an object in motion and the initial velocity and the acceleration asking you for displacement. In that case, this equation here with time is not going to help you because time was not given. This will not help you because time is not given. Here will not help you because time is not given. This is the only equation that will help you because it does not have the time factor. So this is the situation where you have to know the equations and then see what are the given information, and you see which of these four equations will best help you arrive to the answer. But before we delve into the equations, we first have to define what is displacement, what is velocity, what is initial velocity and final velocity, and the net velocity, what is the acceleration, what is time. So when we look at objects that are passing by and, able to carry us from one place to another, if you're inside the airplane, or if you're inside a car, or if you are riding a bicycle, or if you are in a spaceship, you really will never be able to get an assessment of or an evaluation of your motion, except that there is a frame of reference, a comparative frame of reference that you compare yourself to. A man on the island seeing a ship that is sailing past the island will assume that the ship is moving and the island is not. The island is stationary and static, while the ship is moving and dynamic. And the people on the cruise, on the ship, may assume that if they didn't have the knowledge that they are on a ship, they may, if they were just to wake up from, that they are disoriented, or maybe they were in a coma, they have no idea where they are, and they are taken out from the cruise to the surface, and now they see that there's the ocean, and then they see the island. They will think that the island is moving while they are at a stop. So that shows you we need a comparative frame of reference, that we compare our motion relative to that motion. So you have very reliable technology that can get you, I mean, across the globe. You can circumvent the globe in about 48 hours and that could have been impossible, in years ago. And that is because we are able to, we are able to increase the speed, and therefore we can modulate the distance in the given time that we are in. Okay, so for example, here the question is, are clouds a useful reference frame for airplane passengers? Well, that doesn't make sense because clouds themselves are moving. So you need a stationary frame of reference, but then they also discovered that sometimes you need a moving frame of there are two types of frames of reference. There is a stationary static frame of reference, and then there is a dynamic or moving frame of reference to which we compare our movement. But are clouds a useful reference? Obviously not, because clouds are gases and they're constantly moving. So we need to, in order for us to assess our movement in an airplane, we need to compare it to the ground maybe and see how far are we from the ground. Have we crossed the ocean? Have we crossed the river? And Galileo is scientist who was able to develop the importance of this frame of reference. And he thought of it as a stationary frame of reference. But later in physics, we learned the importance of a moving. We need to also have a moving frame of reference. Now, when we want to understand the displacement, you have D with this little O. That is not N-A-U-G-H-T. So N-O-U-G-H-T. Sorry, that's a not. N-O-U-G-H-T. That's the initial or not. So whenever you see VI or V naught, that is the initial velocity or the initial displacement or the initial time. So if you're driving your car from your home to school, it says that your total change in position is measured from your house to your school. So that is here, this could represent the distance. So if the school is a mile away from your home, the distance you travel going to the school is 1 mile. Coming back from the school, that's 2 miles. You have covered a distance of 2 miles going to school in the morning and coming back from school in the afternoon. That is 2 miles. But your displacement, when you headed to the school, your distance was you crossed 1 mile and your displacement was also 1 mile. But in the afternoon, your distance was 2 miles and your displacement was 0. So that here introduces the importance of scalars versus vectors. So vectors have both a magnitude and a direction, while the distance only has a magnitude. So the distance is how much distance did you cover. You went 1 mile to school and 1 mile back. The distance is 2 miles. But the displacement is how far away are you from your initial position. So you started off at the school, you started off at the home, you went to school, that's 1 mile. So your distance, you crossed 1 mile, your displacement, you are 1 mile away from your D naught, where you started, that's another mile. So that's 1 mile. So here your distance and displacement are equal. When you return, your distance is 2 miles, but your final position is your return to the home. So you are zero units away from your initial position. So heading to your school, that could be a positive direction. But coming back in the opposite direction, that must have a different direction. So if you're going to school, that's the positive direction. Coming back from school, that's the negative direction. So you went to school plus 1 mile. You came back from school in the opposite direction, minus 1 mile. You add both of them. That's a 0. So the final position is going to be minus. So you came back in the opposite direction. So that is -1. So the displacement is initial. The displacement is the final position minus the initial. So the final displacement is -1 minus the initial on distance was +1. So -1 minus +1, that comes out to a 0. So the final position was a 0. The initial position was a 0. So you started off from here, your home, it's a 0. You return back to your home. So it's a 0. Your final displacement is, your final position is 0. Initial position is 0. 0 minus 0 is 0. But if you were at the school, you started off at a 0. You ended up the school +1. So your displacement is +1 minus 0. That's +1. So your displacement is +1 miles away from your home. Returning is a 0. So a short line separates the starting and the ending points of this motion. So let's examine now, you're going in a zigzag line. Now, there's a difference here. In a zigzag line, you're going to cover every inch, every step that you took, every meter, every mile, every inch, every foot. So that is going to, you add up the sum of all the distance that you covered. But displacement, you only look at the initial position and the final. The final position is the shortest distance from the initial position. So if the home is a mile away from your friend's home, that means the displacement is 1 mile. But if that 1 mile you kept zigzagging it, you add up in distance, you add up all the steps. But in displacement, it is only the shortest line between is the shortest distance between your initial position and your final position. So the total distance that your car travels is 10 kilometers. But you see, so 5 kilometers to school, 5 kilometers back, the distance is 10. But the displacement, you started off at 0, you went to school, that's +5. You came back to school, that's -5, that's a 0. So the initial, so that shows you that this is west and east. You cannot have them both at the same direction. East can be the positive direction and west is the minus direction. And you need to be, you can reverse the charge, you can reverse you could reverse the polarity, you could reverse the signs. If the west could be positive, east could be negative, but for convenience, we know in our coordinate plane we have north as plus and south as minus and east as plus and west as minus. So if you are traveling 2 kilometers to the east, that's +2 kilometers. And then if you move back, so can we read from this diagram? Can we tell what happened in the journey? So D naught, we said that's your starting position. So this trip went to the west, to the left, 3 kilometers. So the car or the person went 3 kilometers to the west. That's -3. Then they reversed direction and went back towards the initial position, which is in the eastern direction plus. So they went +2. So now, what is the distance? Well, the distance was 3 kilometers to the west, 2 kilometers to the east. That's 5 kilometers. But the displacement is D naught is my position, so that's a 0. My final position is I am here. So I am 1 kilometer away from my initial position in the negative direction. So I am one, so this is divided into 3 kilometers, 1 kilometer, 2 kilometers, 3 kilometers. So now I am my final position is at -1. My initial position is 0. So this on my displacement is -1. -0, that's a -1. I am a kilometer to the west of where I started off. So we use the same basic physics formulas to calculate physics laws, whether in space or in Earth. And that is what shows that physics has a universal component to it, that it could be applied everywhere, in space, in the ocean, on Earth, in the mountain. Physics is physics. So that shows you here another diagram. You should be able to interpret the diagram. Now, during a 30-minute round trip to the store, that's the store, the 30-minute round trip. So that's the total trip was 30 minutes. Could have went there in 10 minutes and came back in another 20, or could have went there in 29 minutes, came back in a minute. We don't know the details, but all we know is that the entire trip time was about 30 minutes. And the total distance covered is 6 kilometers, going in one direction, 3 kilometers, coming in the opposite direction, 3 kilometers. So that is how we calculate the average speed. So the average speed is the total distance, which is 6, divided by the total time it took. So we have 0.5, 30 minutes is 0.5 of an hour. So that is 6 kilometers divided by divided by 0.5, which is the same thing as 12 kilometers, 12 kilometers per hour, 12 kilometers per hour. But the displacement, we started off at the home, that's 0, and we return to the home. So our final position is now the home, D naught, 0. My initial position is D naught, 0. So there is no net change in position. We started at home, we returned to home. So that's a 0. So now let's look at this diagram now. The diagram shows a more detailed record of an airplane passenger heading toward the back of the plane, showing smaller segments. So the D naught is where we start. That's the seat of the plane, the passenger. So there's the passenger is as the D naught. DF is where they ended. Now let's look. In the beginning, the passenger's first trip was from D naught to DA. So they stopped here. Maybe they had a conversation with a friend at this location. Then they continued to another trip. This is the DB. So they ended at trip A here. DB was they went further to this position here. Then they had a third trip, which was they moved back a couple of seats and had another conversation with another passenger here. Then they decided to maybe go all the way to the back to use the bathroom, and that is the third trip, DD. In the end, you must be able to recognize that I started off at D naught, DI, the initial position where the passenger started, and the passenger ended up at the bathroom, for example, at DF, D final. So if you want to calculate the total displacement, you subtract the final. You begin with the final. The bathroom location, that is the negative direction. Remember, we said at the coordinate system, the north, that's the plus y, the east is the plus x, and the south is the minus y, and the west is the minus x. So moving to the left, that's minus. Moving to the right, that's plus. So if we want to know our displacement, we have moved to the left. So now we are at minus. This is the minus position. And this was the D naught. So our displacement is going to definitely be with a minus charge, with a minus sign. Okay, so this diagram shows our y equals mx plus b, where y here represents our distance that we covered vertically, and m is the slope, which is the rise, the change in the y direction, versus the run, which is the distance in the x direction, and b is the y-intercept. Where does our journey cut or intercept or y axis? Now, the slope is here referred to as the m. So the change in the y direction, known as the rise, how far up do we go, divided by the run. How vertically do we move up or how vertically do we move down? That's going to represent the rise, divided by the run, which is moving to the left or moving to the right, moving to the left or moving to the right. That would be, so moving horizontally, anywhere in the horizontally, that's the run. Moving vertically, that is the rise. So rise over run. Okay, a graph of position versus time for the drive to school is shown here. What would the graph look like if we added the return trip? So that shows, look at this graph. The graph has an independent versus dependent variable. The independent variable here is the time. The time does not change. It does not depend on anything. You will always have a 1 minute, 2 minute, 3 minute, 4 minute, but the position is going to change. Maybe in the first 2 minutes you were speeding. At the fourth minute, there's a traffic light, you had to stop. Then, so it is the position who's always going to be the dependent variable. So on the y-axis is our changing dependent variable, while on the x-axis, that is our independent variable. So what does this line show you? That line shows you that this trip took about 10 minutes and we covered about 5 kilometers distance. And we already know that the slope is the rise over the run. And who's our rise? It's position. And who's our run is time. Interesting. What do we get when we divide position by time? Distance by time, that's speed. So now we can conveniently say that the rise in position divided by the run of the time, that is the slope of this position versus time graph. So we can comfortably say that the slope of the position versus time graph is your speed, because position divided by time is the speed. And we know that the rise divided by the run is the slope. So the slope of position versus time graph is the speed. So when you divide 1 kilometer position by 2 minutes, that's going to be 0.5. So the speed at this point was 0.5 kilometers per minute. Then, if you want to get the average speed, then you take the whole distance that we covered, that is 5 kilometers, and you divide it by the whole time it took, 10 minutes. So 5 divided by 10, that is 0.5 kilometers per minute. Okay, so that shows us, we know that y equals mx plus b, so we can modify this graph to have the distance that we covered in the y direction, and we know that our y direction is position. So the total distance we covered is going to equal to d naught. D naught is going to be the initial position from where our trip started. So right here, so we began our trip here, D naught. So D naught is going to be our y-intercept where we started the trip, and we add to that the velocity. The velocity, we know that the velocity is obviously the displacement divided by the time, which is the slope. So we go up 2,000, that's the rise, the slope is the change in displacement, which is 2,000 here divided by the run, which is about 6.4 seconds. So 2,000 divided by 6.4 seconds, 2,000 meters divided by 6.4 seconds, that is the slope, which is the same thing as the velocity. And then we multiply by the time. So the whole time was 6.4. So we replace 6.4 seconds in the t. We multiply that by the slope. The slope is the slope of our graph is going to be 2,000 divided by the 6.4 seconds. And then we add all of that to our y-intercept, which is, we began at 400 kilometers distance. And that will give us actually where we ended. This is the y. So in order to get here, this point, where we ended the trip, we have to multiply where we started the trip. And we have to have where we started the trip, and we add to that the velocity, which is the slope of this graph multiplied by the time of the whole trip. So this shows you now, the diagram shows a graph of the position of a jet-powered car during a time span when it is speeding up. So the slope of a distance versus time graph is velocity. So you know distance versus time, if you divide the rise distance by time, rise over time, or distance divided by time, that's going to be speed. So displacement divided by time is going to be velocity. So the tangential line, what is the tangential line? The tangential line represents the instantaneous, at that instant, the instantaneous velocity. So if you just divide the total distance or displacement covered divided by the total time of the trip, that will give you the average velocity. But if you want the exact velocity at the particular instant, like what was the velocity when we were 10 minutes or we were 10 seconds into our trip? What was our velocity when we were 20 seconds into our trip? That is going to be calculated when we get the tangential line of that particular point. So that particular point is on the x-axis, you have about 15 here. You have 15 seconds, and the y-axis is 1,000. So we get the slope. The slope is 1,000 divided by 15. So 1,000 divided by 15, that's going to be the slope, and the tangential line to this point right here, that is going to represent the instantaneous velocity. So that's how we speed up. We speed up is, in kinematics, we don't study the causes of motion. We just study the motion itself, how fast and how rapidly how rapidly the object is moving. So that's another important graph. That's position versus time graph. So the position versus time graph, what's the slope of that? So position divided by time, that's distance divided by time, that speed, that speed. So here shows you that this trip took about 70 seconds and we traveled 20 minutes in the 20 seconds. So if we want the average speed, then we gather the whole distance covered, which is up here, 20 meters. We divided by the whole time it took 70. So 20 divided by 70, that is the average speed for the whole trip. But the graph could also show you at 30 minutes, we covered 10 meters. At 10 minutes, we covered 5 meters. At 50 seconds, we covered 15 meters. So you should be able to interpret and read the graph. That's another exponential graph showing us the instantaneous um, distance divided by time. That's velocity. So the tangential line here is going to show me this point shows me the exact velocity or the exact speed at 10 seconds. So you must understand that the tangential line to a point on the position versus time graph would represent the instantaneous speed or the instantaneous velocity. Now let's look at this very interesting trip. Now, what does this trip show you? This trip shows us that the whole trip took about 20 minutes because we started at 0, we ended at 20. So D naught or DI is a 0. And I'm sorry, the TI or T naught, the beginning time was a 0, and the finish time, TF, the final time is a 20. So the whole trip took 20 minutes. So just by looking at this graph, you should be able to tell that the whole trip took about 20 minutes. Now, position. You should be able to tell that the highest distance that we covered was about 5 kilometers because the graph ends at 5. Didn't go up to 6 or 7, didn't end at 4 or 3, it ended at 5. So we covered a distance of 5 kilometers. Now the question is, what happened? What happens here is that the direction of our position has ended. We moved up. Remember, we said the y-axis going up, that's positive, coming down, that's negative. That shows you for 10 minutes, we went in the positive direction. The positive direction could be going north, going east, going south, going west. It doesn't matter. But what matters is you have to understand that after minute 10, we went in exactly the opposite direction of our initial trip. So from minute 0 to minute 1, so from minute 0 to minute 2, we went 1 kilometer in one direction. From minute 0 to minute 4, we went 2 kilometers on that same direction. From minute 0 to minute 10, we went about 5 kilometers on one direction. Then maybe that person forgot their cell phone or forgot their something that's very important. They need to go right home. So they took the exit and went down the other direction. So from minute 10 to minute 12, now we went back 1 whole kilometer. Then from minute 12 to minute 14, we went back 2 kilometers. And then by the time it was 20 minutes, we returned back to D naught. We returned back to our initial position. So that shows you, this graph shows you that we have traveled. So a question would be, what is happening at minute 10? You say that there is a reversal of direction. What happens at minute 8? You see that we have covered about 4 kilometers in 8 minutes. Now let's look at this graph. So here you don't have distance versus time. You have velocity versus time. So what could be the slope of this graph now? Velocity versus time. So if velocity is our rise, time is our run, what is velocity divided by time? That's acceleration. So the slope of a graph that has velocity as the rise, velocity versus time graph, that the slope of that graph would definitely be the acceleration. Well, here we don't have a slope. If you see, there's a straight line. So that means there's zero acceleration. It means we did not accelerate. And the only way we get a zero acceleration is when the velocity is constant, when the velocity is the same. So you're driving with the same velocity. It could be you didn't even start your car. Your initial velocity is zero, your final velocity is zero, then your acceleration is zero, because zero divided by anything is zero. If you're driving at 7 miles per hour, for 5 minutes, you're just at 7 miles per hour. So your final velocity is 7 miles per hour. Your initial velocity is 7 miles per hour. 7 minus 7 is zero, so no acceleration. Acceleration only represents change in speed. So that's the graph of velocity versus time. So now let's explain what's happening here. So you see that in 10 minutes, something very strange happened. In 10 minutes, we started with a velocity of 0.5 kilometers per minute. We kept this velocity. We're driving 0.5 kilometers per minute for 1 minute, for 2 minutes. So for an entire 10-minute trip, we were driving exactly at 0.5 kilometers per minute. Then at 10 minutes, we stopped. Then the graph moved down. So now we're not moving at 0.5 kilometers per minute. We're moving at minus 0.5 kilometers per minute. What does that tell you? That tells you we changed direction. So we were headed 0.5 kilometers per minute in the north direction here. But here we still going 0.5 kilometers per minute, but in the south. That's why the sign changed. Here we were going in the north, now we're going in the south. Here we're going in the east, now we're going in the west. So the velocity here did not change the magnitude. We're still driving at 0.5 kilometers per minute, but we're driving at a different direction because the velocity has both a magnitude and a direction, a magnitude and a direction. Okay, so this graph here shows you displacement versus time. So what is the slope of displacement versus time? Displacement divided by time, that is acceleration. So the slope here, so the whole general, the average acceleration is going to be the whole displacement that we took divided by all the time that took for the trip. So the trip took 30 minutes, 30 seconds, I'm sorry, 30 seconds, and the displacement was 3,000 meters. So we divided 3,000 by 3,000 divided by 30 seconds. That's going to give you displacement divided by time. That is the velocity. That will give you the average velocity. But if I do not want the average velocity, I want the velocity at, for example, a particular instant of time, like here when I'm at 20 seconds or 10 seconds, then what I got to do here is I have to get the tangential line. I have to get the slope of the tangential line here. You see, I have to get this point, I have to make a line that is tangential to the point, and then this line, I have to get its slope. The slope of that tangential line will represent the instantaneous velocity of that particular point. So that shows us here the same thing, rise over run. So the velocity divided by time. So now what is the slope of this graph? Now you have velocity divided by time. That's acceleration. So the rise over run. So if you want to get the average acceleration, you get the whole velocity that we covered, 160 meters per second, and you divide it by how many seconds the trip took. The trip took 30 seconds. You divide 160 by 30. That will give you the average acceleration. But if you want the instantaneous acceleration, you make a tangential line to the point and you get the rise over the run of that point, and that will give you the instantaneous acceleration of that point. The same thing here. That's the instantaneous acceleration when we make a tangential line to this point and we divide our rise, which happens to be the velocity, the change in velocity, divided by our run, the change in the time. So this trip here, what can we learn about this trip? we learned that the trip took about an entire, for example, 24 seconds. And from the beginning until about 4 seconds, our velocity increased up to 3 meters per second. Then we maintained the same exact velocity for about up to 20 seconds, and then we started to drop our velocity, to decrease our velocity, and our velocity is decreasing, but we are moving, our velocity is decreasing. So we had velocity 3 meters per second, and now it is dropping to 2, but we are moving in the same direction. Otherwise, if we move down here to the negative, that would represent if the velocity sign changed, that means you have changed the direction. But since here everything is up in the positive quadrant here on the first quadrant of our graph, then that means we are changing our velocity, but we're changing the magnitude of our velocity, but we are not changing the sign or the direction of our velocity. Okay, that shows us the same thing. So that shows us the a trip for position versus time. In position versus time, that's distance versus time, that's speed. So you know the trip here took about 10 seconds. And for the first 4 seconds, the runner was increasing the speed. But when the runner reached 4 seconds, the runner maintained the speed of 12 meters per second. If you want the instantaneous speed, you have to get the tangential line. You have to get the slope of the tangential line to that particular point. And we do the same thing here. We have discussed that. Okay. So that shows you what happened on the trips. So if you go from one trip to another, you have to be careful about the time and always recognize your your independent variable is always the time. Your dependent variable may be the velocity, may be the displacement, may be the speed, may be the position. Doesn't matter. What matters is remember that the slope is the rise, which is the y change in the y-axis divided by the change in the x-axis. And you know that distance divided by time is speed. Velocity divided by time is acceleration. Displacement divided by time is velocity. And distance divided by time is speed. Okay, we have discussed that. So here we see that we began here at 8 or 9 meters away. Then we returned back. Then we deviated about. So that's if that's our initial position, then we have moved in the negative direction about this much. Then we return back and we stopped here. So if you want the distance, you add all the time, all the distance that has been measured, has been covered. But for displacement, you look at the final position, that's here. You subtract the initial position from it, and that will give you the answer. Okay, so here the car is, so here for acceleration, the car, here you see the acceleration is in the same direction of the velocity. So here the car is speeding up and the acceleration in the same direction. So you know the car is gonna go even faster. But here the car is speeding up in this direction in the east, but the acceleration is in the opposite direction. Now you know we're pressing the brake and the velocity is gonna drop. So the acceleration always affects the velocity if their direction is the same. If the velocity and acceleration both are minus, you're going to have increase in the minus direction. If the velocity and acceleration are both plus, you're going to have increase in the plus direction. But if one is minus, one is plus, or if one is plus, one is minus, you know you're going to have deceleration or so you see slowing down in B because both of them are inverse and speeding up in A because both of them are in the same direction. Okay. So here our initial velocity is 0. Our final velocity is 30 kilometers per hour. If I want my acceleration is the change in velocity, which is the final velocity minus initial velocity. So 30 minus 0 divided by the time, the hour. So that's going to be 30. Our acceleration is going to be 30 kilometers per hour. Here they were in the same direction, but here they are in opposite direction. So my final velocity is a 0, and my initial velocity is plus 30. So 0 minus plus 30, our acceleration is minus 30 kilometers per hour squared. So you do remember the acceleration is velocity divided by um is measured in units, displacement divided by times square. That's the slope of displacement versus time. You know, that's acceleration. Displacement versus time. I'm sorry, displacement divided by time, that is velocity. Velocity divided by time, that's acceleration. So here, that's another calculation of our very important kinematic equations that we began with here. And we're going to learn that not only do we calculate our acceleration from velocity and time, you know that acceleration could also be 2 multiplied by the displacement divided by time squared. That will give you the acceleration. So the slope of 2 multiplied by the displacement divided by the time squared, that will give you acceleration. Also, this formula, the velocity squared multiply, so the velocity squared is the same thing as the meters per second squared. So the slope of the velocity squared divided by 2 multiplied by the displacement, that is also going to give you the acceleration. So it's not just velocity divided by time. It's also velocity squared divided by 2 multiplied by the displacement covered. So that shows you if you throw a rock in the air, the rock is gonna go up with a speed of 13.0 miles an hour, meters per second, and the gravity is gonna pull it in the minus direction with the acceleration of minus 9.8. So it's pulling it down. It's gonna reach a point where the velocity is going to equal 0. Then we're going to accelerate in the opposite direction, minus 9.8.